have a new computer now and a new monitor, so I don't know. I'm still changing settings on trying to get all the settings the way I like it. And when I present, it's a different shape. I used to have like a square monitor, pretty close to square. Now this is one of them skinny, not very tall, real wide. So may have to do some adjustments because I was looking at some of our lesson and it looks really small. So I got to have to blow it up because it's. Uh, I don't know. We'll play with it as we get into there, but just different stuff going on with a new computer and a new monitor to deal with, and all that fun stuff. So anyway, everyone doing well? How's your week going? I mean, here we are sitting on Tuesday. Busy, busy week for me this week and next week. I'm helping my son-in-law. There's a like a little league football thing going on at church, upward football, and he's the photographer. So he does all the sports pictures with all the teams come up. He takes the team photos and individual photos. So I'm helping him with that, like tonight, last night, Thursday night, this week, next week. So don't have a whole lot of time in the evenings either. So that's just going to be a crazy week. But we'll just get used to it and move right along. It's good. I like helping my son-in-law and all this stuff. And little fella, my little man, come visit me last night. I love it because since mommy and daddy are out at the football fields, I just have to show you this picture. I haven't showed it to the other class, but I'm going to show you this picture. Oh, where it is? Oh, it's in my text. My wife sent it to me. Right, right. Oh, my daughter sent it to me. Oh, there was my little guy. He got up in the chair with me, and then we was watching some football together, and then he just went to sleep. He just fell asleep right there, sitting with his pappy. So it's funny. He likes to sit with pappy, and we'll watch TV or just look around the room and talk and all that stuff. And his mom tells me over, and it is dad too. They both tell me he never sits with anyone else. He wants to get down and do something. He never sits with anybody. He doesn't sit with mom, doesn't sit with dad. He just sits with me. I'm the only person he wants to sit with. He'll just sit there next to me and just be all happy for half an hour at a time, which is just crazy. But yeah, my little man, little happy guy, fun stuff. All right, now we've just about got everybody in here. Closer, closer, closer. All right, I have some tests to grade. I noticed that there's people turned it in. I haven't got a grade yet. I got some graded last week that were turned in earlier in the week. There are still, let's see, quite a number of them that have not been graded. One, two, three, four, five. So it looks like seven. I have seven tests to grade. The part two stuff. The part one should have been graded automatically in Buzz, but a part two. And then I see there's still about five people that have yet to complete the test. So don't get real far behind, folks. Don't give it now. If you haven't finished some of the work from the unit, do that before you take the test because that you need to know that stuff on the test. So don't just skip all the earlier stuff. Oh, I got to get the test done. Let me skip all that. Well, you're not going to do well in the test because you skipped all that, right? So don't do that. But get work on getting caught up. And those of you who've got it turned in, I'll get it graded. I'll get it, I'll have it by Friday. I'll have it in the grade book even. So I'll get it graded and get it in the grade book. But I'll be working on that this week. So with that said, let's get to looking at what we have this week. Let me get it up on my screen so I can present it here. And this unit is going to look a little different than last unit in Buzz. And I can talk about that before I present that. Um, Algebra 3 is kind of a unique class in the fact that Arkansas has Algebra 3, but a lot of states don't do Algebra 3. They go into different courses. They do. Now, what we cover in Algebra 3 is covered in those other states. They just call it different classes. And so Arkansas defines Algebra 3 and says Algebra 3 is going to cover these subjects. So in Buzz, we've pulled together all the subjects Algebra 3 are, but we've pulled them from different classes that existed. Like some of this is some Algebra 2 stuff that some of the courses cover. This unit is actually pulled from a pre-calculus textbook. I have a textbook That's calculus, pre-calculus, and it covers a lot. In other states, this would be like a pre-calculus class, where it's an algebra 3 class here. And so I have copied some of those pages from the textbook for us to use for this unit. And so some of the units will look normal like Buzz with all the pages. This is just one long page because I've just copied all of it to one long document and uploaded it to Buzz. So it's going to look different. And I'll show you how it works. And what we cover, the textbook, the way it does it is it does like a page or two of an overview of the lesson. Here is everything that's in this lesson, right? So there'll be a couple of pages of here's everything we're going to study, and then as you scroll down the page, it gets into more detail, and it's like, oh, now let's actually study that, and you go detailed and little fine details all the way down to the bottom. During class, we go over that overview. We'll spend time looking at the summary of everything that's in that lesson. You can go down if you don't get it and don't understand from what we cover. Of course, you can always ask me as well, but you can scroll down the lesson to. We don't have time to cover all the detail to get into. You can go and look at more examples further down the page where they may have a better explanation that you may get it that you didn't get what we were talking about in class. I mean, we try to cover it as solid as we can right here in class. So I'm not saying we're going to skip part of the definitions. We're going to cover all the definitions and make sure we understand all the what it's talking about. But it just has more information as you go down the screen. So if you're struggling with something, read the rest of the lesson. See if that helps you. Come ask me if it helps you. If there's something you don't understand on this. But I've been using this for a few years. Generally, students do really well. Do really well with it. So don't fret and freak out about it. But if it looks different, that's why. Because I've had to pull it from a calculus textbook because it's what we cover in Algebra 3, which not every state has Algebra 3. So with that, let's put it up on the screen so we can see. All right, what are you talking about, Mr. Brock? Well, I'll have to show you. Okay, looking at this, going to our grade screen, we are done with Module 1. We had the test last week. Like I said, some of you I have to get grades in. Some of you have not turned it in yet. But, don't skip anything. Get everything done. You should have grades for everything in Module 1, or at least submitted, even if I don't have it graded yet. So, but if that's where you're behind, you need to get caught up on that. We're going to start Module 2. Analyzing functions now. Analyzing functions. This week, September 21st is Sunday. We're going to look at 2.01 and 2.02, functions and their properties and graphs of functions. And then we'll have a couple of lessons next week. And then first week of October, we'll have one lesson and we can go ahead and do the practice test. And then we'll have the test right after that. So we're going to spend about 3 weeks. Look at this one. We spent 3 or 4 weeks. Look at the last one. But 2.01, 2.02 this week. Let's go back to the activity screen. Open up this folder now. And I'll show you how this lesson looks. Like I said, it's a little different because it's one long document. This is a long Google Doc I put together and loaded here. See, so this has the scenic overlook. This is where it like summarizes everything we're going to look at. And it goes down. And then there's the actual textbook lesson. So we're gonna cover these 2 pages, which is basically a summary, a big picture view of everything in the lesson, and then here's where it gets into more. This looks more like a textbook. The little graphs and illustrations and all of that kind of stuff. But there is extra information with sample problems. They put a lot of sample problems down here. Find the range of this function. And so then they put it on a graph and talk all about it and how you do it. And then you can confirm it algebraically. So there is the entire lesson. But like I said, we're going to cover the scenic overview. And this looks really small on the screen. It worked fine on my square screen, but they got this new one. So I'm going to blow this up bigger where it looks better on our page. That ought to be pretty good there. I'll blow up too big. We won't be able to see much up and down is the problem with that. So move that thing over there. Okay, Functions in the property. So most situations we encounter in our lives follow a cause and effect relationship. If we try to do something, there will be a result. In mathematics, that rule of correspondence is known as a function. So some examples of that function are, here's functions in our lives, right? If we drive on interstate at 70 miles an hour while going to Yosemite National Park, how far would we travel in a given number of hours? Right? If we're driving 70 miles an hour and we drive for 2 hours, how far did we make it? Just as an aside, if you want a good laugh, you can find videos on YouTube. I remember seeing this one where this guy, and I don't know if it's his wife or his girlfriend, but they're like in their 20s, they're young, and he says, okay, so we're driving 60 miles an hour. How long will we? How far will we go in 1 hour? And she's over there just really thinking about it. Is it 40 miles? Is it, and really play? It's like it's a very very simple math problem, but she's struggling, and it's funny just to watch her reason through it and try to come up with it. She never does come up with 60. If you're going 60 miles per hour, that means in 1 hour you go 60 miles because that's what that means, 60 miles per hour. So it's very amusing. So when I see this problem every time we get to this lesson, if we drive an interstate at 70 miles an hour, how far will we travel in a given number of hours? I always think of that YouTube video with that young lady that really can't figure that out. Can't figure that out at all. If I purchase a certificate of deposit paying 4.5% interest per year, how much would it be worth after a given number of years? Let's say 5 years from now, how much is that worth if it's a 5 year CD? Well, we can calculate that kind of thing. That's a function. If I was hiking on the John Muir, that's a tough one to say, trail, and I could hike 12 and a half miles per day, how far could I hike in a given number of days? After 3 days, how far have I hiked? Those are all functions. And we can create a chart to show these things. Like, look at the 70 miles an hour. We can create a table or a chart uh, where we put the hours on the top line and we put the miles on the second line. So for 1 hour, 70 miles, 2 hours, 140, 3 miles, 210. And, in 10 hours, you've moved a good distance away. You've traveled through a couple of states, probably, unless perhaps you're going through Texas or California, north to south. We could also take this function instead of putting it on a chart or a table, and we could just put it as ordered pairs. Look, the pair 1 comma 70, 2 comma 140, 3 comma 1. So this is basically the X and the Y. All right, the X value is the hours. That's that many hours. The range, the Y is determined by the X. So we can just write all those as points all the way. And this keeps going to 12, 12, 840. So in each ordered pair, the first element is the hours that we traveled. And since we know hours multiplied by the rate equals distance traveled, we can calculate what the second number is in each ordered pair or on our table. So this textbook, like I said, is like a calculus textbook, and it gives a lot of definitions and mathy talk at a college level, right? This is Algebra 3. We're at a higher level. So we're going to read these definitions, and then we'll talk about what that is. It's just like real words, right? I mean, these are real words, but these are like college words that nobody uses sometimes. So we'll see that a lot in these lessons. Definition of a function. A function f from a set A to a set B is a rule of correspondence that assigns to each element x in the set A exactly one element y in set B. The set A is the domain or the set of inputs of the function f, and the set B contains the range or the set of outputs. It's like, whoo, boy, that is real mathy. That's what your college class is going to sound like. A function f from set A to set B is a rule of correspondence that assigns to each element in set A exactly one thing in set B. So the way they'll illustrate that a lot of times in college is like, okay, we've got set A, and they may draw a kind of a bubble. And over here we've got this set In set A, we've got these x's. These are all x's in set A. And over here, we may have a set B. And set B may be 2, 4, 5, and 9. And so it says a function is to where each element in set A is assigned an element in set B. And 2 is going to be assigned to 5, 3 is going to be assigned to 4, 4 is going to be assigned to 9, and 5 is going to be assigned to 2. Each element, each x, these are x's, these are y's, is assigned to exactly one element. There's not two lines. I can't also assign 9, or it's not a function anymore. Right. I can assign two of them to the same y. Look, 1 is 2 and 5 is 2, but still there's only one value associated with 1. There's only one value associated with 5. There's only one value associated with 3. Each of these only has one value assigned to it. It's a function. Function. So that is a higher level look of that, kind of like you'll look at it in college compared to how we look at it in Algebra 1 or Algebra 2. And so the set A is the domain or set of inputs, and the set B contains the range. Yeah, so we can add that in function. This is the domain of our function. This is the range of the function. And this is nothing new. We've always talked about the x values of the domain and the y values of the range. We just have not presented it in this fashion. It's just a different visual, but it means the same thing that we've always said. And the characteristics of functions. All functions have the following characteristics. For each value in the domain, there's only one corresponding value in the range, right? We just saw that. Every x only has one y. Here's another characteristic of a function. All elements in the domain must be used, right? We didn't have like a 6 down here that wasn't assigned to anyone. Everything has to be used in the domain. And more than one value in the domain can be matched with the same value in the range. We saw that too. More than one of the x's was assigned to 2. And that's fine for a function. So those are the primary characteristics for all functions right there. All right, now we have a test your skills. These are practice problems. And I do have this set up where if we want to check our answers, this is working. Oh, this isn't working today. Uh-oh. Oh, here it is. It's right here. Yeah, I clicked it and it showed up right here. I can click this and it has check your answers because I have that as well. It'll load. It takes it a moment to load. We'll come back to it. But let's look at this. Use the set of values 1, 2, 3, 4 as the domain. Okay, so they've given us the domain 1, 2, 3, 4. And here are the values that are the range: -2, -1, 0, 1, and 2. Which of the following ordered pairs represents valid functions? Why or why not? So let's look at these. I'll try to even make them a little bigger here. Yeah, we could do that. Okay. So this is our domain, 1, 2, 3, 4. These are the possible values of the range. Is a valid function? You can put it in the chat, or you can do thumbs up, thumbs down, however you want to do that. Is a valid function? 4, 2, 3, 1, 2, -1, 1, comma, -2. And if you want to review, for each value in the domain, Alexander says yes. For each value in the domain, there's only one value in the range. Natalia's with it. All elements must be used. This is one that may get you. All elements in the domain must be used. And you can attach the same y to more than one x. Okay, let's go back down a little bit. Okay, So we said yes, A is valid. And I believe that's correct. Yeah. Because we used 4, 3, 2, 1. We used all of them, and they're each only assigned to one range. We don't have to use all the range. All right, how about the second one? 2, 1, 4, 1, 1, 0, 3, 0. No? What rule did it break? People are saying no here. Did it use, let's look at this. Did it use all the values? It used 1, 2, 3, and 4. Is any of those values assigned to more than one y? 2, 1, 4, 1, 1, 0, 3, 0. And you can match more than one. So one is assigned to two different x's, but still, that looks like it's still a valid function. Again, did this load? Valid, valid. The first two is valid. Yes. How about this one? 4, -2, 4, -1, 4, 0, 4, 1, 4, 2. Oh, we got all of the range this time. Oh, Alexander says big time no. Luke says no. I'm seeing no in the chat as well. Right. 4 is the only thing we use in the domain, and it got 5 different y's attached to it. 4 different values in the range. That breaks a lot of rules right there. Breaks a lot of rules. It did not use all of the domain, and 4 is assigned multiple values. How about D? 1, -2, 2, -1, 3, 0, 4, 1, and 5, 2. That's a little puzzling, right? Daniel says, I don't think that's valid function. Alexander agrees with you. Then we've got this 5 here that's not part of our domain. So if we look at our answers, and it's hard to look at our answers, is not valid. It includes an element that is not in the domain stated above. Right. Yeah, that's got number that's not even part of our domain. Let's see. E. 1 goes to -2, 2 goes to -1, 3 goes to 0, 3 goes to 1, 4 goes to negative, 4 goes to +2. No, this one's a little easier, right? It was looking good until 3 got listed twice. 3 is 0 and 3 is 1. It can't be both. It's not a function. How about 1, 1, 2, 2, 3, 1, 4, 2? Yeah, that's fine. 1, 2, 3, 4 is just paired up with 1 and 2 and 1 and 2. Again, it duplicates the range values. It only uses 1 and 2, but only 1 is given to each of those. And we'll look at the answers. Valid, valid. Those 3 are not valid. The element 3 is matched with 2 elements. And the last one is valid. So, yeah, we're right. C, D, and E were not valid. Not valid at all. So, good job. Good job. All right. Let's see what else. Functions in algebra. So in algebra, we are familiar with expressions or formulas that we represent with an equation. Often, the set of ordered pairs can be shown as an equation with 2 variables. For example, the equation y equals 2x plus 1 creates ordered pairs for the value of x. So for every x we substitute in there, we'll get a value of y, or as it says, a value that is derived for y. Got to use our college speech in this. If the domain is 1, 2, 3, right, and we can select the domain, then the range would be 3, 5, 7. Because for 1, 2 times 1 plus 1 would be 3. 2 times 2 plus 1 would be 5. 3 times 2 plus 1 would be 7. So whatever x that we put into that function, we get out one y value, and that becomes the range that goes with the chosen domain. The x variable, and we don't talk about this nearly enough, the x variable is called the independent variable because we get to choose what x we want to use. We get to choose our x. So it's independent. It doesn't depend on anything. I'm going to say let's put in 5 for x. But the y variable is called the dependent variable because the only way we know what y is, well, that depends on what x is. It's dependent. It's a dependent variable. So when we talk about dependent or independent, you have to think about how do we get the number. We don't solve this to figure out what x was. We choose an x. We just independently pick something. I want x to be 10. Okay, well, if x is 10, then the y is going to be 21. The y depends on whatever you say x is. So what is the y in this equation? Well, I don't know. That depends on what x is. Tell me what x is, and I can give you a y. That's the easiest way to think about dependent and independent, right? The y is definitely going to depend on what the x value is. So, for example, let me get this to scroll down just a touch. What would the range be for the equation y equals 7 minus 3x if the domain is integer values such that -4 is less than x, which is less than 3? So basically, x is every integer between -4 and 3, but does not include -4 and 3 because it doesn't say equals to. It just says less than. So that means the range, the domain would be -3, -2, -1, 0, 1, and 2. Just integers. It says integer values. So since it's just integers, we don't include -4 because it's less than or equal to that, but we go to the next integer, -3, -2, -1. So there are 6 values in the domain. And using those 6 values, we can determine what the range is by just substituting those into the equation. 7 minus 3 times -3. Well, that'd be 7 minus -9. So it'd be 7 plus 9 or 16. That'd be the first value in the range. So we can determine the range if we know what the domain is and what the equation is. So here are 4 more check your answer problems. Let me get the answers loading because that takes it a minute. Here's a nice start. Y equals 2x, where 10 is less than x and less than 20. So basically all the x's, and we're going to assume, because I think it probably assumes over here too, that those are, no, I guess it doesn't have to assume it's integers. Every x between 10 and 20, not including 10 or 20. So the range would be what? The range would be every y between 10 and 20. So we would write this would be the range. Since our domain is every x between 10 and 20, and our equation is y equals x, if that's all the x's, when we substitute, okay, x equals 10.96. Put it in the equation. Oh, y equals 10.96 because y equals whatever x is. So the range is going to be exactly the same as the domain. Exactly the same. Y equals 2x, where x is all the numbers between the 10 and 20, the infinite number of numbers between 10 and 20. So our range, looking at 2x, it's just double, right? So it's going to be all the y's between 20 and 40. 21.38642. Right, because it's going to be twice as large as the x. How about this one? Y equals x squared, where -3 is less than x is less than 3. Think about that and put something in the chat. What would the range be for y equals x squared when our selected domain is everything between -3 and 3? We see what you're thinking on that. You can get that if you put a little thought into it. What are the possible range? What's the possible range if we substitute numbers that are between -3 and 3 into that equation? That'll give you the range. Your first instinct is, okay, I'll just square. Because if I'm choosing every x that's greater than 9, but not including 9, and every x that's less than 9 and not including 9, you've left no room for any numbers. Unless you include 9. Then you just have one number in the range. And we know that's not right. So this one's a little interesting when we think about the possible range. And it's a lot easier to think of the range if you think of what the graph looks like. So if I take the graph of this right here, y equals x squared, we know it looks like this. Right? It's y equals x squared. It's a parabola, and it goes through the origin because it's just x squared. And if we cut it off between 3 and -3, we know that this up here is going to be 9. We know that this up here is going to be 9 at that point. Those 2 points are going to be at 9 because -3 squared is 9, 3 squared is 9. What is the range? What are all the y's? So the range, we know at the top end, less than 9, not equal to, because we didn't include 3. 3 is not part of it. It stops. So let me put a hollow circle. Hollow circles right there. It does not include 9 because we're not taking 3. We are including 2.99999 repeating. So we're going to get really, really close to 9, as close as could infinitely be possible. But what about the other side? What's our lowest? Well, as x gets closer to 0, and in fact includes 0, because it includes every number in between there, 0 is our smallest. And it includes 0. Oh, I gotta move that over. We can see all that. Y equals x squared. The range would be 0 included, everything greater than or including 0 up to 9. See, that one fooled us a little bit. We got used to the linear stuff, and this threw us a little bit of a loop. So yeah, think about the graph and say, oh yeah, the range would be, everything from here to here. This is the range. This is how much y's are included in that. And yes, 0 is included because 0 is in our domain. 0 is in between there, so 0 squared is 0. Oh, it's a good one. I like that one a lot. That's good. How about this one? Determine the range for this equation. The equation is y equals 5, and the x's are going to be everything between 10 and 20. So what is the range? Oh, Eileen's quick with an answer. You want to think of the graph of that one? Let's see. We can graph that. Y equals 5. Oh, I didn't click it. Y equals 5. There's the graph. It's that green line. But we only want, let's see, the x's between 10 and 20, right? Okay, we'll only graph those. So let me go down. Oh, I used parentheses and brackets. Hold on. There you go. There's the graph of only the x's between 10 and 20 of the line y equals 5. Take out these minor grid lines, just step 1. So Eileen's got it exactly. The range is 5. It doesn't go higher than 5. It doesn't go below 5. It only includes 5. That's the only y's that are in there. Check our answers. 10 to 20, 20 to 40. 0 greater than or equal to y is less than 9. And the range is just 5 because it doesn't matter what the x is. The y is always 5. The x can be any of those numbers, but the y never changes. The y is always 5. All right. Function notation. Now, we know what function notation is. Let's see how they explain it. In our previous example, we determined the value of y based on values assigned to x. Another way to say this is that y is a function of x. So we denote this as y equals f of x, function of x. So we say y is a function of x. Therefore, our example equation could be written as f of x equals 7 minus 3x, right? Where they put y equals 7 minus 3x up here, that's the same thing as f of x equals 7 minus 3x. And we understand this. We've been doing that since Algebra 1. For each value of x in the domain, we can calculate the value of f at x. Then from that example, the value of f at x equals negative 3 would be 16. Because 7 minus 3 times negative 3 would make it a positive 9 plus 7, 16. I show it right there. 7 minus 3 times negative 3. So determine the value of f at x, f at x, for the function f of x equals 7 minus 3x. For x equals negative 3. Okay, we just did that. It was 16. How about when x equals 10? See, this should allow me to pull up the answers on this as well. Check your answers. Right there. All right. Calculate these. B, C, and D. We did A right above. It's 16. But what is it when x equals 10? For 7 minus 3 of x. The function is f of x equals 7 minus 3x. So f of 10 equals what? Daniel's got an answer. He says it's 23. Do we have agreements from anyone? Do we have a different answer from anyone? Oh, guess I'm going to have to write this down because we're getting confused. Oh, Soraya's got a different answer. Looks very similar, but it is different. Let's see. F of x equals 7 minus 3x. F of 10 would be 7 minus 3 times 10, which is 7 minus 30. It is negative 23. Don't forget about our negatives. That little thing we figured out in our head, sometimes we forget, oh yeah, I'm subtracting 30. This answer is actually a negative. All right, negative 23. C is x equals 0. So what is f of x when x equals 0? That one's probably easier to do in our head too. When x is 0, that makes things pretty simple. Paisley's quick on that one. So is that one. Right. Yes. It'd be 7 minus 3 times 0. And we know anything times 0 is just 0. So what is 7 minus 0? Yeah, that equals 7. How about when x equals negative 10? When x equals negative 10. That's very similar to what we had up here, except for now there's a negative sign in play. All right. Oh, you guys are watching on this. Owen Paisley Alexander, Sarai. Yes, if it's negative 10, negative 3 times negative 10 would be a positive 30. So we got 7 plus 30. It is 37. So if we check our answers over here, 16, negative 23, positive 7, positive 37. Great job. So yeah, when you go through this, if one of these isn't working, let me know because I try to make sure all these check your answers are working. The domain of a function. Let's see. The domain of a function can be all the valid values for the expression that defines the function. For example, the domain of f of x equals 1 minus x is all real numbers. Well, let's see, what does that look like? F of x, come on. Can I type it as f of x in Desmos? Equals 1 minus x. Yeah, it doesn't matter if we type f of x. 1 minus x. So there's the graph of 1 minus x. And if we look to see, well, what is the domain? What are the x's that it covers? Well, if we keep scrolling out, we see there's a lot of x's. Look at there. We've got all the way to like negative 60,000 to positive 60,000. Oh, 120,000. Oh, wait, there's 200,000. Yeah, it goes forever, right? It's negative infinity to infinity, negative infinity to infinity, which we can simply write as all real numbers because it also includes uh, all the decimals in between there. So all real numbers is the easiest way to say that. Every number, because it goes forever in both directions to infinity and negative infinity. For f of x equals 1 over 1 minus x, the domain would be all real numbers except 1. Because if x equals 1, 1 minus 1, it'd be dividing by 0. If we look at a graph of that, 1 divided by 1 minus x, delete this. Look, we have an asymptote at x equals 1. This goes all the way towards negative infinity as x gets closer to 1. As it gets smaller and smaller, gets closer and closer to 1, it drops. Over here, as it gets closer to 1 from the negative values, it goes up and up and up. But it never, x equals 1, it never touches that x equals 1 line. It just gets really, really close. We have to zoom in to see the difference. But there is a difference. Look, they separate. Since a domain is a set of real numbers, the domain of f of x equals the square root of x is x is greater than or equals 0. So let's take a look at that. The square root of x. Notice I typed SQRT and it automatically put a square root. You can also go down and hit their square root button they have at the bottom of the page. But I can't see the graph because I'm in the wrong place. Let me zoom out. Let me get back where I'm supposed to be up here. Ooh. Oh, there's the graph. So yes, it does include 0. 0, 0 is part of the graph because the square root of 0 is 0. It does not include any negative numbers because we can't take the square root of a negative number. That's imaginary. You have to have a whole different graph to graph imaginary numbers. So a domain is a set of real numbers. The domain of that is x is greater than or equal to 0. You can review internal notation, interval notation. Okay, I don't have that link working. Interval notation. But we could Google that if we need to. All right, now it wants us to determine the domains of these equations right here. What is the domain of f of x equals the square root of 20 minus 2x? Oh, that looks interesting. F of x equals the square root. You're like, how would we calculate that? How would we calculate that? So I'll put that on paper just so we can kind of play with it just a little bit. We'll grab a different pencil. That was a scraggly pencil. So if we think about it, we know that this number cannot be a negative number, whatever this calculates to be, right? Because it's a square root. We can't have a square root that's a negative number. So we know, this is a nice way to do it, kind of looking at how calculus would do this. 20 minus 2x has to be greater than or equal to 0, right? Whatever this calculates to be underneath there has to be 0 or bigger. It can be 0, but it could be bigger. So any number bigger than that, which means if we move this over, negative 2x is greater than or equal to negative 20. Now, let me show you something, and it's not going to go into this in this lesson. I'm really kind of giving you a preview calculus lesson, or an area we're not covering. If instead of an equal sign, since we have a greater than equal sign, if we divide by a negative number, which we need to do, divide by a negative, that causes something to happen. You must flip the greater than or equal to. So this means x is less than or equal to 10. Because we divided by a negative. Anytime you divide by a negative and you're doing this kind of math with a greater than or a less than, you have to flip it. Could there be a problem that includes all whole numbers but not decimals? There could be. We're not playing with that. It depends on, we would have to define it that way. If we define the domain as integers. With these equations, no, we can, unless we define it to be integers. And that would, again, x is the independent variable, so we can select the x's. In these equations, they're not defining them as integers, so it's any x's that work mathematically in this case. So this says any x less than or equal to 10. So we need to graph this and see why would this be less than or equal to 10. It was showing greater than or equal, but we flipped it. Is that right? Well, let's take a look at the graph of this problem. So instead of x, the square root of 20, what is it, minus 2x. Oh, looky there. The graph of this equation, 20 minus 2x, includes all the x's that are smaller than or equal to 10, which is exactly what we calculated. All the x's smaller than or equal to 10 would be included in the domain of this equation. It's like, why would that be? Well, let's test one. Let's just go f of x equals square root of 20 minus 2 times 11. I'm going to go bigger than 10 because I'm like, I think I can go bigger because this doesn't make sense to flip this. So the square root of 20 minus 2 times 11. Oh, wait a minute. Now I've got the square root of a negative 2. Yeah, that doesn't work. I can't get a number bigger than 10. See, I can always test it. If I'm not sure if I'm right, test it. Do one on each side. Let's do square root of 20 minus 2 times 9. Maybe I can't figure out for sure. Should this be less than or greater than 10? Because I could have just done this equal to 0. If I'd done it equal to 0, let's say, okay, x equals, this is the border. X equals 10. But does it include all the x's smaller than 10, or does it include the x's larger than 10? Well, 20 minus 2 times 9 is 20 minus 18. Yeah, this is legal. So smaller than 10 is good. Larger than 10 creates a problem because we have the square root of a negative number. Because, yeah, I could just say, okay, when would this be 0? When would it be 0? Well, it'd be 0 when x equals 10. So then, if this is 0 when x equals 10, do I want all the x's less than that, or do I want all the x's larger than that? And I can just test it this way. I don't have to play with flipping the negative and none of that. I can just ignore that until equals. Then just figure out which way do I need to go. And this has to be less than, because when we're Down here at 9, it's the square root of 2, which is 1.41421, et cetera, et cetera, et cetera, et cetera, et cetera. Determine the domain of this 5 over x minus 2. Okay, what would that domain be? What x's are legal with 5 divided by x minus 2? Is it all real numbers? Can I put any x? Let me graph it. 5 over x minus 2. 5 divided by parentheses x minus 2. There's the graph. Goes all the way to negative infinity. Goes all the way to infinity on the x's. What's going on here? There must be an x that it cannot be. What is that x? If x equals 2, what is our equation? All right, good job, guys. If x equals 2, 5 divided by 2 minus 2 is 0. 5 divided by 0. Yeah, it can't be 2. It can be less than 2. Look, it can be 1, 0, negative 4.8, or negative 5.44. It can be any number less than 2. It could be anything larger than 2. Look, it could be 5.57. It could be 12.65, 22.27. It could even be 2.625, 2.371. That's all fine. It can be 1.383, 1.402, 1.49. It can be, it just cannot be 2. So basically, it's all real numbers, and they probably write this in a fancy college way too, except x cannot be 2. So we can say that all real numbers, comma, but x cannot be 2. That's what this is saying. It can be anything but 2. No 2. No 2 allowed. And we see that here. It's every number. It's all the way to infinity. It's all the way to negative infinity. It's just, it's not 2. There's an asymptote there. X equals 2. That red line, it never touches that red line. That's an asymptote. How about the area of a square with side S? Oh, I like that. So if we have an equation that calculates the area of a square that has a side S, what's the domain? The area will be the range. What's the area of our square? Which means the independent value, the x value, the domain value is going to be S. How long is the side of your square? So what are the possible x's in that situation? I'd like to say we're thinking outside the box, but actually we're literally thinking about a box. So if I have a square, side S, we're going to say these are all the same, even if I didn't draw it exactly right. What limits are there on S? Can S be negative 10? Because that's what my tape measure said. I measured the side, and that side of that square was negative 10. This looks a lot more rectangular on the screen than it does on my paper. So that means my camera must be a little wonky or something. All right. Can S be 47? What's the limitations on S right there? If we look at that, it cannot be a negative number. Your tape measure, when you measure the square, your tape measure, your ruler, whatever you're using, does not have any negative measurements on there. I have, wow, I got, for someone who teaches virtually, I have a lot of rulers. I have 1, 2, 3, 4, 5, 6, 7 rulers here. I have 7 rulers. And let me check. No, no. Flip that one over. No, no. Not one of them has a negative measurement. I can't measure a negative square. Not one of these rulers allows me to measure a negative number. So that kind of limits us right there. But did I check our answers on this? No, I haven't. And then we have this parabola, which is easiest to graph. Negative, yeah, let's graph that first. Y equals 3x squared. Negative 3x squared. Oh, it's negative. Negative 3x squared. Plus 2x plus 12. Well, that it's easy to see that our, what's what we find? The domain, this is going to keep going to negative infinity. This is going to go to positive infinity. It just goes down really fast, but it'll keep getting wider and wider and wider and wider and wider. So the domain is all real numbers. Now the range is not. The range is what's the largest one they got? That's the largest. It's all the y's less than or equal to 12.3333 repeating, but the domain is forever. So let's look here. X is less than or equal to 10. We calculated that for this square root one. X is not equal to 2. We said it could be any number except 2. And look, the side is greater than 0. If the side length is 0, you don't have a square. You don't have a square. There's no area because you don't have a square. But as long as the side length is larger than 0, again, no negative numbers, and then all real numbers on that last that goes to negative infinity to infinity, all real numbers. And that is the end of the lesson because now we're down to their summary they give. I want to make it smaller. We can see more of that. This is where they get more into this function definition and notation. So they define it again. This shows the mapping of A to B, like I did on paper. Definition of the function. Does formula y equals x squared define y as a function of x? Like I say, this gives more examples. Here's some graphs of some of these. Talks about the vertical line test. And we know the vertical line test for a function. If you can draw a straight up and down line and it does not touch the function more than once, it's a function. So there's a little bit of extra information down there. Let's look at the assignment that goes with this first lesson. Then we need to look at our second lesson, which should go quicker. It needs to. Determine whether this graph is the graph of a function. That's the vertical line test. And it looks like it's linear. It's just a line. What's the domain of this function? Again, you may want to graph it and take a look and see. What's the domain of this function? Oh, that's a little trickier. It's got two numbers on the denominator. What's the range? Okay, we got out of the domain. This was domain. This was domain. This one's range. What's the range? What are the possible y's? Like this one is everything less than or equal to 12.333. Oh, and we have one fill in the blank. Determine whether the formula describes y as a function of x. Explain your reasoning. So I'd go back to, does it meet those three definitions? Is this a function? Does it map one y to every x? And yes, we can use all of the domain. Don't have to worry about that part of the definition. But is there any y, is there any x that has more than one y using this equation right here? So one you have to answer. Now they say 2 points each, but the whole thing is worth 20 points. So I double that. So this is actually worth 4 points. So, okay. Let's go to our other lesson for the week. And it's just about graphs of functions. So I think this will go pretty quick. So this talks about, let me blow this up again. How come it didn't blow up? Oh, it did. There we go. It just took a second. In the preceding section, we looked at functions as numbers from an algebraic viewpoint. Now we're going to look from a graphical viewpoint. We learn to look at the pictures they generate and determine many characteristics of the functions. Using only the picture of a function, we can determine the domain range and some values. So using the graphing utility, I have linked Desmos on here, so you can click here and open Desmos real easily. The graph of a function. Recall that the definition of a function and apply it to a graphical representation. For any given x along a horizontal axis, there will be exactly one y value along the vertical axis. Therefore, any vertical line can intercept the graph of a function only once. The vertical line test for a function states, if the line intersects the curve in more than one place at any point, the curve is not the graph of a function. So let's look at this. Let's make a horizontal line. X equals A. No, I didn't like that. I was trying to make it just like a number that I can play with, but let's just do 3. Oh, here we go. I can play with it this way. So let me go from negative 20 to 20. And if I move, I can move that line left and right. See, I can move it left and right. So as we zoom in on this, and I say, let's make this a red line. Look at the red line. As I move this red line left and right, does it touch this graph more than once in any place? It does not. So this is a function. Let's change this equation to be, first off, let's make it positive. And let's make it a third degree function. Oh, that didn't do it right. Make it a third degree function, minus 2x squared type function. Okay, so that's a third degree function. And if we look at it, does this line touch it anywhere more than once? It does not. But what if we change this to be x equals y? Well, that's a weird graph. Okay, how about this one? Now we've got this graph here. And if we move this, it's like, okay, it's a function, 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 it's not a function. Look, I can touch the graph 3 times if I have a vertical line at x equals 11.4. Okay, so this is not a function because it failed the vertical line test. I can hit that graph 3 times. If I'm over here, I can hit the graph twice. I can hit it right there at that point where it touches right there and down here. But anywhere, it just takes one place that it fails and it's not a function. So study the graph of a function helps you to understand the function. So here's an example they give. Oh, so we're going to add these terms in there too. Increasing, decreasing, increasing. Relative maximum, relative minimum. So below are the formal definitions of increasing, decreasing constant functions. All right, I like this. This gets into a college definition. Definition of increasing. When x is between x1 and x2, that implies that f of x1 is less than f of x2. It's like, what? Like I say, college, we get into some real interesting definitions in math and use some interesting terminology. But that says, in a nutshell, and we're going to live in a nutshell for a while. Let's go up here. Let's make our graph. So it said between x1 and x2. So this is x1, this is x2. Whatever that is. This may be -8, -4, whatever it is. Between there, it says if it's increasing, f of x1, right, which means the y value at that point, this right here, f of x1, is going to be less than f of x2. If we substitute x2 in, and the y is going to be right there. So it says that this is less than that. Well, it is. It's down here at a negative number, and this is up at a positive number. So this is a less than that. So that means this is increasing. Increasing. And when we look on a graph, we can see it's increasing. It's increasing all the way to right there. This is an increasing graph. That's all increasing. Now, at that point, it stops increasing and it's flat just at that one point. And then it's going to be decreasing until it gets down to here. Because when we look at this, if I look at this x and this x, the y value is up here, the y value is down here. This one's greater than this one. It's decreasing. Between those two x's. Between whatever x this is and whatever x this is, it's decreasing during that interval. And then after this x, it's increasing again. Increasing also here and here. We have two places. Boy, that's a terrible arrow. We have two places that this graph is increasing. One place it's decreasing. And then they also use the term, like this point right here is a relative minimum. That means if you look on either side, the graph is higher. The y is larger on either side of this point. It's not very big, larger, but on either side, it's larger. And this point up here is, as you would expect, a relative maximum. Because on either side of that point, the y's are smaller. Now, here's the thing. Why do I call it a relative minimum? That means just relative to this part of the graph. This is the smallest possible range, the smallest possible y, relatively speaking, which means just in this area. Because if I look at the whole graph, that's not the smallest y. It goes down to negative infinity. There's a whole bunch of y's over here that are a lot smaller. And this is not the largest point on the graph because this graph goes up to infinity. This goes forever. So these are not the maximum and minimum. They're only relatively the maximum, relatively the minimum if I ignore other parts of the graph. So I'm just talking about a relative minimum and a relative maximum, just relatively speaking, not completely speaking. There is no max, no min, because it goes to infinity. And it goes to negative infinity. So every time you give me a number that's the maximum, I can give you that number plus one that's still on the graph, and it's not a maximum, no minimum. But relatively speaking, there is. That's the difference. That's the understanding what that means. And they show that right here, a relative max and a relative min. Increasing, decreasing, increasing. And so they show this. We can see the function is increasing for x is less than negative 1.5. This is the point where x is negative 1.5. So less than that, the graph is increasing because we always look from left to right, left to right. It's increasing until it gets to 1.5. And after x is greater than 1.5, which is over here, it's increasing again. But between negative 1.5 and 1.5, this graph is decreasing. Just right in that section, it's decreasing. Just between there. Now notice it doesn't include, it's not equal because at negative 1.5, it's flat. That's the part where it's not going up, it's not going down, it's just level. All right. So x1 less than x2 implies that the y values at those two places are less. So that means it's decreasing. So this is the mathy definition of increasing and decreasing. X1 is less than x2 implies that f of x1 is less than f of x2. So a function f is increasing on an interval if for any given x1 and x2 in the interval, x1 less than x2 implies that the function is x1 is less than the function of x2. That just means as the x values increase, so do the corresponding y values. As x gets bigger, this is increasing because the y's are getting bigger. This is increasing the entire time. The y's are always getting bigger as they, well, this goes backward. That's kind of weird. This is not a function. We're talking about functions. Let's talk about a function. This one's not a function. A constant function. We can put a constant function on there. Y equals 2. That green line is a constant function. It's not increasing, nor is it decreasing. It is staying at 2 all the time. It's constant function. So know what that means. A constant function is not increasing nor decreasing. All the y's stay the same. Look, f of x1 equals f of x2 for any x1 and x2 on the interval that it's constant. Relative minimum, relative maximums, we just looked at that. Here's the mathy definition. Here's the college definition of that. A function value f of a is called a relative minimum of f if there exists an interval of x1, x2, which means we're only looking at part of the graph. In this interval, where x is between x1, x2, that means f of a, this one point, is less than or equal to every value between those intervals. When we substitute x into f of x, this point a, that's the minimum, is smaller than all the other ones around it. Smaller than all the ones around it, which we see when we do y equals x squared. You know, this is the minimum because on either side of it, if we get just a little bit bigger than 0, at 0.2, the y is 0.04. It's not 0. If we go on the other side, 0.16. See, it's never less than 0. Even at 0.1, it's 0.01. So this is the smallest point. And on this graph, it's the absolute minimum. Nowhere is it less than that. So, all right, but it's a low point if it's a minimum. It's a relative maximum if it's a high point on the graph. They look like a local high point. But here is the college definition of that, if we want to go through that. Using the graph to find relative extrema. Extrema. Look at the graph above. Oh, see, I did put a link to that. Oh, it didn't like that. Okay, forget that. Look at the graph above. So it goes back up to this graph. There we go. And there's a relative minimum at x equals 1.5, a relative maximum at negative 1.5. Relative maximum minimums can be found using the trace key on your calculator or on Desmos just by following that along there. That's the same thing the trace key does in your calculator. You can trace it as it goes along to find what the values are. And the value is, oh, look right there. There's the values. That's what they're talking about. Symmetry. Oh, let's talk about symmetry. Symmetry with respect to the y-axis. This has symmetry to the y-axis because let me put the y-axis line on there. It's that blue line, right? That blue line, and that's a mirror image. It's a mirror image to the right and to the left, right? Symmetry. That means it's exactly the same on both sides, like a mirror creates. A mirror creates an image that's exactly the same. So this has symmetry to the y-axis. If I change the equation to be x equals y squared, it's not a function, but this equation has symmetry to the y-axis. I mean, to the x-axis, sorry. This has symmetry to the y-axis. The sideways one has symmetry to the x-axis because it's exactly the same distance up here as it is down here. Exactly the same distance, both directions for that graph as you go top and bottom. The symmetry of the y-axis is right here. Now, there's another kind of symmetry we can have. Let me turn those off. Is you can have symmetry to the origin with an equation like this. Let me make it more extreme. No, that doesn't have the symmetry. Never mind. This is symmetry to the origin, which means if you take this part of the graph and rotate it 180 degrees, it's exactly the same as this. Oh, I think I can make it more extreme. There you go. Every point over here can be found over here as well, just by taking the opposite. Like this is the point 2, 6. That means the point -2, -6 is there. Same point, just 180 degrees difference. Instead of 2 positives, it's got 2 negatives. This point, instead of having a positive and a negative, it'll have a negative and a positive with the same numbers. See, same numbers, but it's 180 degrees around the origin. So this is called origin symmetry because it rotates 180 degrees around the origin. So with that, a graph with symmetry with respect to the y-axis is whenever xy is on the graph, you have the point x negative x y. So with that y equals x squared graph that had symmetry to the y-axis, when I have the point over here, that's the point 2, 4, I also have the point -2, 4. Where's it at? Where's it at? It's running from me. There it is, -2, 4. Because it's the same distance. This is to this direction. This is to this direction. The y-axis looks like a mirror for the graph. A graph has symmetry with respect to the origin is whenever you have x, y, you also have negative x, negative y, which we saw 2, 6 and -2, -6. Rotational symmetry, they call it, because the graph can be rotated 180 degrees around the origin. And then the graph with symmetry to the x-axis, whenever you have x, y, you got x, negative y. So if you have 2, 4, you have 2, -4. So let's talk about an even or an odd function. An even or an odd function. And I'm not talking about here, I need to define this. Even function. Does not mean it uses even numbers. Not. It doesn't mean it's using all even numbers, right? Oh, so Mr. Brock, that means 2x to the fourth minus 4x squared plus 6 is an even function. Because it's got all even numbers, 2s and 4s and 6s. No, that does not mean it's an even function. In the same respect, odd functions, same thing. Does not mean it uses odd numbers. Not. I didn't write the whole thing out that time, but say same. No, let's look at what it does mean. A function whose graph is symmetric with respect to the y-axis is an even function. That means this is considered an even function. Even if it's 3x squared. 3x squared. It's got a 3 in there. That's an odd number. This is got symmetry to the y-axis. Even equals symmetry to y-axis. And I'll show you that. I wrote it quickly and sloppily, unfortunately, but even means symmetry to the y-axis. Odd means rotational symmetry to origin. By rotational, we mean 180 degrees. This is what odd functions and even functions. When we graph them, if it's symmetric to the y-axis, it's an even function. If it has rotational 180 degree symmetry to the origin, it's an odd function. Let's see. A function whose graph is symmetric with respect to the origins of the odd function. The graph of a non-zero function cannot be symmetric with the x-axis. Why? Why can it not be symmetric to the x-axis? There's an even function. There's an odd function. But if it's symmetric with the x-axis, let's make one. That's symmetric with the x-axis. It's not a function. That's why a function cannot be symmetric to the x-axis, because it fails that. Put this line. See, it fails the vertical line test because it has two y's, not a function. That's the answer there. Why? Because it is not a function. A test. Here's a test. Let's see. What else do we have to cover in here? Because we're running. Got 10 minutes left. Oh, that's the end of the lesson. Okay. Okay. Here's a test. So I'm going to show this on paper. Test for even and odd. Boy, my writing's got to get better. Test for even and odd. Substitute negative x. Okay. So if we have f of x equals 2x squared minus 3. And we're trying to figure out, is this an even or an odd function or neither? It'll tell us either way. Substitute negative x in. So f of negative x equals 2 times negative x squared minus 3. Now notice only the x is squared, not the 2. So what does this equal? What is negative x squared? Negative x times negative x. That equals x squared. So negative times a negative. So this equals 2x squared minus 3. Oh, wait a minute. And that's when we substituted negative x in there. So f of negative x equals the exact same thing that f of x does. Same. So this is an even function. Since that ended up the exact same, when I substitute negative x in, I got the exact same equation I started with. All right, let's try this. 4x to the third plus x. I'm going to test to see, is this an even function? So I substitute negative x in. F of negative x. So 4 times negative x to the third power plus negative x. Everywhere there was an x, we substituted. So f of negative x equals, what is negative x to the third power? Negative x times negative x times negative x. Well, negative x times negative x, we know is x squared. But when we multiply x squared times another x, now we're back to a negative, and it's negative x to the third. So this is 4 times negative x to the third. Plus a negative x means minus x. So f of negative x equals negative 4x to the third minus x. Oh, notice here, let's see if I have a lighter kind of highlighter there. This has a negative, that has a negative. This was a positive, this was a positive. Everything's opposite. every term opposite sign. Every term that has the opposite sign. This is an odd function. Well, this is great for our notes right here, guys. If we substitute negative x, which we did here as well, we substituted negative x, and it ends up exactly the same as the original. Every term, -3, +2x squared, everything. This is an even function. If we substitute negative x, and this was a positive term and a positive term, this is a negative term and the negative term, everything changed. If this would have been a plus and a minus, and this is a minus and a plus, that's still every term is the opposite sign. This is an odd function. Let's test one more. Let's say it's 3x to the third plus 2x squared minus 1. And we're going to substitute negative x in. So this is 3 times negative x to the third plus 2 times negative x squared minus 1. When we simplify that, we know negative x to the third is just negative x to the third. We've calculated that here. So this ends up negative 3x to the third. Negative x squared is a positive. So this ends up 2x squared, and minus 1 is just minus 1. No, this was a negative 3, right? Because this was negative x to the third, so negative 3x to the third. So what happened here? We had this one and this one ended up exactly the same. They were both positive and negative. Now they're both. This one was a positive up here, but it's a negative down here. So from there to there, some terms the same, some opposite. Sometimes the same, some opposite. Neither, oh, make it better, neither even nor odd. So you're going to be able, need to be able to do that on a test or a quiz or something. I don't remember where we see this, but I do remember this is on a test question where it gives you an equation and says determine if it's even or odd by substituting negative x. So you just put negative x in there and then just simplify it and compare. When I simplified this, it ended up exactly the same as what it started. When I simplified this, it ended up exactly the opposite sign of every term. So it's odd. This one had some change from positive to negative. Some of them stayed the same term they were. These stayed positive. These stayed. So this is neither even nor odd. It does not have symmetry to the origin. It does not have symmetry to the y-axis. It kind of does a little bit of each. So that's what that means. If you substitute f of x, you end up with the opposite term of everything of f of x. This one, you end up with f of x again. Let's look at the assignment. We're out of time. Let me determine the intervals on when this is increasing and decreasing and constant. Is it increasing when x is less than 0 and decreasing when it's greater? Or is it just the opposite of that? Or is it increasing at 3 or decreasing? Use the graph of f to estimate what is the local maximum and the local minimum. And they give you 4 choices. Does this have a local minimum, local maximum? Determine algebraically by substituting. Is this even, odd, or neither one? Substitute negative x and find out, do I end up with exactly the same, exactly the opposite, or a combination? And, oh, here you go. Give an example of an even function and explain algebraically, which means not graphing, it means putting negative x in there, and you get to make up the function. And some of you, it will ask for an even function, some of you, it will ask for an odd function, and some of you, it may ask for one that's neither one. So pay attention to what's asking you, and you get to give the, and remember, use this insert equation button. Instead of putting 3x to the third plus 4x squared minus 1 equals 0, instead of putting it like that, use this insert equation button and make it look like that. Make it look right, not looking all jumbled up. I mean, that gets hard to read. You can read it, but it gets hard to read the more of it you have. This looks real easy to read. All right, guys, that's our 2 assignments. That's our 2 lessons. That's the whole kit and caboodle, as they say. I don't know what a caboodle looks like, but if you had the whole thing, I guess you'd know. All right, this is an A day Friday, so we'll have class on Thursday if you need to come see me as we get in this new unit. If you're not finished with last unit, do the assignments before you take the test if you're missing any assignments, but get that turned in soon because we're moving on away from systems of equations and other things or whatever we were reviewing algebra last time. Yeah, so we're on to our new stuff here. Have a great week. Email me if you got questions or come see me Thursday.